Hi, I'm Dr. Matthew Michal. I am a lecturer of mathematics at NGIT in Newark, New Jersey. So I'm showing and walking through a series of PowerPoint presentations put together by the 10th edition of Boyce and DePrima textbook. That was awkward. By the Boyce and DePrima 10th edition textbook. These are PowerPoint slides based on the text. So I'm walking through it, trying to teach my students how to think about reading the textbook and learn from it. I'm going to be showing you different techniques to think about that. But today we're going to be talking about how to solve things numerically. So all this chapter, on chapter 2, we've been solving first order linear systems. The idea that the derivative dy dt is equal to some rate function which has some initial condition that y is equal to the value of y naught, a constant, when time, or t, is equal to t naught. Now, if my rate function, f, as well as the partial derivative f sub y is continuous, then we're going to have a unique solution about that time interval. So that's important because in some cases, because if we have that, we know we're going to get a solution. But here's the problem. Sometimes we aren't going to be able to solve it in our typical analytic techniques. And so earlier on in chapter 1, we talked about the idea of direction fields. Now, the first equation that you see there and the second equation you see there are both maybe solvable. I think we solve both of these. But especially in the case of the second one, that's going to be a complicated looking thing. That might be difficult to actually solve. So what we might need to do is we might need to have a different approach to try to find these solutions that could be quite complicated and that do not have nice analytical or algebraic methods. So to deal with that, we're going to be basing everything based off of different techniques that we saw in Calc 1. Not even Calc 2, but Calc 1. It's going to be using the idea of tangent lines, hence why this method is sometimes called the tangent line method. But more historically, we typically call it Euler's method, Euler's method to help solve this. What we're going to do is we're going to use the fact that f of ty is the slope of the graph. It is where is the graph going. And if I know where I currently am, my current y value and my current t value, and I know the slope of the graph at that point, I can predict or approximate what the next value of the function is going to be based on how far in time I want to travel. So we make a tangent line. Remember, the definition of the tangent line is y is equal to y naught plus a slope t minus t naught. Well, I know what the slope is at that point. I know what the y value is. I know what the t value is. So it depends. How far do you want to travel? Well, pick a certain t1 value that I'm going to travel from here to here. So what I'm going to do is I'm going to approximate a new y1 after a one step, so that's y1. This is my approximation of this point. At t is equal to 1, I'm estimating that my solution is right here. Again, choose another point, t2, that I'm going to approximate for y2. But here's the thing. I know all the rate functions. I know because I have a function f of t, y. So plugging in my t1, plugging in my y1, predict what the slope is at this new point. So using a tangent line, y2 is equal to y1 plus the slope times t2 minus t1. And so on, and so on, and so on. And if to make things easier, frequently what we're going to do is choose a uniform step size. For example, let's always take a step size of 0.1 seconds, or 0.1 milliseconds, or 0.1 nanoseconds, or 0.05 seconds, assuming that uniform step size, and assuming that we're going to call this Fn, that's going to be the rate function at Tn, Yn, or at time step n and y at time step n. The next time step is going to be y sub n plus 1, the next time, based on the current value of y plus the current slope times your step size. And we do this over and over and over again. Why not? With a slope, we're going to take a step size of 0.2. So, there we are, in our new y1. At y1, we get a different slope, a little bit less, same step size. Moving on up. New y2, calculated slope. Oh, this time it's flat. So, move over flat. Straight over to t is equal to 0.6. New y3. New slope goes up a little. Move that forward in time. New, I think this is y4. Yeah, y4. Calculate and move on. And notice that each time we move on, the calculation, the approximation is going to be a little bit farther off and a little bit farther off. And, that's to be expected to some extent. But also notice it's going to be harder and harder to calculate. So this method is really useful when using a computer, a calculator, something that's able to do this in a very quick manner. And we know what the solution of this graph is because we've already solved it in section 2.1. So we can approximate how far off we were. Turns out, not bad. Yeah, we have a little bit of an error, right? Roughly 10% error, but that's pretty darn close. And it gives us a general idea of where we're going. And when equations start looking even worse than this, more complicated, like what happens if I put a y squared here? Because it's no longer linear, I can't use integrating factors anymore. Stuff like that could be really useful solving and using these techniques. And so, watch what happens when I use different step sizes and compare it at t is equal to 1, 2, 3, 4, and 5 with our real solution to the differential equation. Look, even with a time step of 0.1 seconds or 0.1 units, right? That's pretty darn close, even after 5 units of time has passed. And when we do 0.01, wow, that is remarkably close to 2 decimal places, maybe even higher. So the smaller the step size, the better we're going to be, the closer the approximation we're going to do. But also do keep in mind, I had to make 10 times the number of steps in order to get the same information. So you're playing, are you willing to pay 10 more time steps in order to get the same amount of information? Yes, it'll be more accurate, but is 10 times the steps worth it? I don't know. That's a decision you have to make. In equations like this, that might be worth it, or it might not be worth it, because, but eventually you have to make the decision, I no longer have the resources, or it's not time effective in order to do all these time steps. Do keep in mind that these are approximations and that things can go terribly, terribly wrong. That's why I'm mentioning that you want to keep in mind small time steps are key. The smaller your time steps, the closer it is to your actual graph. That's going to be very, very useful. I mean, converging families of solutions. If I can predict that my solutions are going to have negative roots, yeah, it's not going to matter as much as you're going to get closer and closer. But for divergent families, families where the solutions have positive roots, a small variance in the wrong way could cause serious issues. So, I mean, you might be traveling along this path here, but if your step size is a little bit too big, or say right here on the borderline, right about here, if your time step is just a little bit too big, if I step too far over, I can go from a diverging to positive infinity solution to a diverging to negative infinity solution. So be careful. But these techniques are very useful, and I get very excited when I see this because, you know, these solutions of this form, I mean, you see it all over the place. Got very excited in the movie that came out recently, Hidden Figures. Now I just stated this video. But I got very excited because in the movie they actually specifically mentioned this method. A lot of modern day approximation methods are built on the Euler approximation. So it's very powerful, very useful. We have better now, but it's all based on this approximation to this method.